Hello everyone. Welcome to the presentation for robust category level 3D pose estimation from Diffusion-Enhanced synthetic data in WACV 2024. Category level 3D pose estimation aims to determine the 3D orientation of objects within a general category, rather than specific instances. However, obtaining well-annotated data for this task is difficult, as it involves detailed and accurate labeling across a wide range of object variations within each category. Our motivation in this work is to overcome the high cost and complexity of annotating 3D object poses in real-world data. By generating synthetic data through a graphics-guided diffusion model, we aim to create high-quality datasets for model training. Additionally, we're developing an unsupervised domain adaptation strategy to close the performance gap between models trained on synthetic data and those relying on extensively annotated real-world data. Our approach learns 3D pose estimation from our synthetic dataset P3D diffusion, where CAD models are rendered under randomly sampled viewpoints. Additionally, we applied diffusion models to transfer the style of synthetic images while maintaining 3D consistencies. To address out-of-distribution challenges, our OOD-aware generation method breaks the spurious correlations between task-related semantic information and domain-specific background features. Using P3D diffusion, we propose CC3D that allows for accurate 3D pose estimation on real data, even in challenging domains considered to be out of distribution for standard benchmarks. The P3D diffusion dataset generating involves a graphics-guided style transfer module. It starts with a rendered image from CAD models using a graphics-based renderer. A canny edge detector then creates a 2D edge map that holds the object's semantic and structural details. This edge map guides the generative model to produce high-quality, realistic images. The method ensures semantic and structural integrity is maintained, leading to accurate 3D annotations. To address mode collapse seen in early experiments, where objects lack texture and varied colors, two strategies are employed. One involves rendering CAD models with textures, introducing consistent prior noise to the edge maps, prompting the model to generate diverse textures. The other strategy is prompt engineering, which involves adding random colors to the style transfer prompts, ensuring a broad color spectrum while preserving 3D consistency. Our OOD-aware approach enhances the model's adaptability to unfamiliar data by decoupling essential object traits from background variations. It achieves this by diversifying backgrounds in our synthetic dataset, helping the model to focus on the object's core features. This technique is key for better performance on out-of-distribution data. Our work significantly builds upon neural mesh models, which learn generative models for feature activations and are used for solving object 3D poses through an analysis by synthesis approach. Neural mesh models represent objects as a neural mesh consisting of a set of vertices that form a cuboid mesh, along with learnable features for each vertex. Our model integrates three types of losses: contrastive loss, which improves the distinctiveness of features by differentiating between foreground and background elements; reconstruction loss, focusing on minimizing errors in feature reconstruction to accurately infer object poses; and domain consistency loss, which ensures feature consistency across synthetic and real images to enhance the model's ability to generalize across different domains. Unsupervised domain adaptation in our model uses pseudo-labels to bridge the gap between synthetic training data and real-world data. We first train the neural mesh on synthetic data. For unlabeled real data, we predict poses and assess their quality using a self-consistency check based on render and compare techniques. The top-performing images are selected as pseudo-labels for fine-tuning. Our CC3D model demonstrates remarkable results in 3D pose estimation on the Pascal 3D Plus dataset. When annotations of real images are not available, our proposed CC3D outperforms the NeMo and ResNet 50 baselines that use same training data by a significant margin. When annotations of real images are available, our model outperforms the fully supervised state-of-the-art by 10.4% at pi/18 accuracy, using only 50% of the annotated data. The OODCV dataset includes out-of-distribution examples from 10 categories in Pascal 3D+. This dataset is specifically designed to assess out-of-distribution robustness against factors like pose, shape, texture, context, and weather. CC3D's performance on this benchmark highlights its robustness and adaptability to diverse and challenging real-world conditions, outperforming other models when trained without real annotations or fine-tuned with a small portion of real data. In summary, we've introduced diffusion-enhanced synthetic data and the CC3D algorithm, which reduce the domain gap to fully supervised models. Our approach is shown to outperform previous state-of-the-art models with only minimal real annotations and stands out in handling challenging out-of-distribution scenarios. That's all for this presentation. Thanks for watching this video.